Over the past 5 years, I repaired and modified countless, mostly broken objects that I had found on scrapyards, in thrift stores, or on online marketplaces. And I have documented a lot of that here on YouTube. While doing that, I was always also planning to build bigger machines, reusing many useful parts that I had been able to salvage over the years. Among those things was a set of 2 identical, massive linear guides with trapezoidal screws, as well as this huge ball screw here that some company must have dumped on one of the scrapyards. And since this is an incredibly expensive part, I'm not quite sure why it ended up on the scrap. I also found all kinds of stock materials, like massive I-beams, as well as flat stock and steel tubes, metal sheets and steel plates of various sizes and shapes that I had collected here over the years. Throughout the series, we also collected big stepper motors from various industrial applications, as well as other parts that could be used for automation purposes. I also found aluminium round stock, old window well grates, and bought additional parts like linear guides of different shapes. I collected many of these parts over a span of several years because I was always planning to build some CNC machines for the workshop sooner or later. Then, 3 months ago, I felt like I was finally at a point where I could begin to actually turn those plans into a physical reality. So I spent some money to buy the missing parts. I repaired a big plasma cutter from the 1980s and also constructed a powerful air compressor from mostly scrap parts to go along with it. Using a TIG welder that I had just fixed at the same time, a steel frame was built and a small CNC plasma table was constructed from mostly used parts to go along with the newly repaired plasma cutter. While the smaller unit isn't really finished yet, it was brought to a point of basic functionality where we can use it to make parts with it. If you are interested in seeing those repairs and builds, the videos are linked under this episode here. On top of building that smaller plasma CNC table, the last episode also covered some preliminary work for the multimodal CNC machine, the building process of which we're going to cover here today. So let me sum up what happened so far. So what we basically did is to haul a bunch of I-beams around, remove rust using various methods, cutting these beams into sections and creating 2 weldments that were then bolted to the I-beam sections in the middle. This way it'll later be possible to disassemble the entire machine in case I have to move in the future. The next step was now to figure out how exactly the heavy screws and linear guides will be attached on top of this support made from I-beams. They will be bolted down rather than welded for 2 reasons. 1, so that the device can be disassembled again in the future. And 2, it also must be possible to adjust the exact positions of the components later on to create a near perfect alignment for the linear guides. Otherwise, the motors will have to work against each other and the resulting milling and cutting operations would not be very precise. If we just welded everything in place right now, we will be unable to adjust the alignment later on. For the purpose of bolting down the 2 identical trapezoidal screw guide units to the surface of the bench, I proceeded by fabricating a number of rectangular parts from 10mm flat stock. The parts were scribed, cut with an angle grinder and deburred using a bench grinder. Before a number of holes were then drilled, by means of which the guides will be fastened to the underlying structure. These longer sections of flat stock here will also be welded to the support structures on the left and right hand side. They will later be bolted to the I-beam sections in the middle, however. But since it was super tough to drill all those holes by hand in the last episode, I will only do this once I have obtained a mag-based drill, which will happen in the near future, hopefully. The 10mm thick steel plate sections will also act as spacers so that the cast iron parts that hold the nuts riding on those screws can move freely. For the time being, these linear guide assemblies will be held down by big screw clamps. I did my best to align them as precisely as possible, but their actual final position will only be determined once the entire moving apparatus of this machine is complete and has been tested. The mounting holes in the support structure will only be drilled then. It is very important that everything will be able to move smoothly and without any tension or stresses. And after this was done on both sides of the table, it was now time to decide how to connect our two identical stepper motors to the two screws. Since both the screws and the steppers were used in conjunction with tooth belts in their first life, I decided to use tooth belts in this application as well. The problem, of course, was that the pulleys that came with the motors are not compatible with the pulleys sitting on the ends of those screws. The first thought was to reuse these massive pulleys that the screws came with. They had some surface rust and some dented and missing flanges, but those are all things that I could take care of. The bigger questions were what kind of tooth belts they were made for back in the day, if belts would be available at all, if I would be able to obtain 2 more pulleys that would fit the shafts of those steppers, and if so, what that would cost me. The first difficulty is to find out what kind of profile the pulleys were actually made for, as there are many different styles. It is rather obvious that it is a simple old-fashioned trapezoidal profile. However, I needed to do some research to confirm that the old pulleys are for non-metric tooth belts, size H, which means that their pitch is 1/2 inch or 12.7 millimeters. That being the distance between the midpoints of 2 adjacent teeth. These pulleys here on the motor shafts also come with a trapezoidal profile. They are metric though, and for a much smaller pitch. So the first idea was to have 2 new pulleys made that fit on the stepper's 14mm axle, but with H profile and 2 short H profile toothed belts. Unfortunately, those 4 parts would cost me almost 165 euros. If this would have been the only thing that I had to spend money on to build this CNC table, I would just have done it. But the project is very expensive and cost me a lot of money every step of the way. So I came up with another plan. Last year I had done some research into a cheap source for pulleys, because this is the kind of problem I run into all the time. What I found are these crankshaft pulleys that were used in older VW cars some 30 years ago. I bought a whole bunch of them as new replacement parts for around $5 a pop. They have a really nice surface finish, and the material they are made of is a joy to work on in the lathe. Their profile is non-metric as well, and they are size L, which means a pitch of 3/8 of an inch or 9.525 millimeters, which is the next smaller size to size H of the original pulleys. They have a 14.5 millimeter bore and 4 M8 threads. Using different methods, I'm able to adapt these cheap mass-produced parts for all kinds of purposes now. So let me show you what I did here. After clamping the pulley into the 3-jaw chuck of my small lathe here, I was able to widen the bore from 14.5 to 20 millimeters using a 16, 18 and then a 20 millimeter drill bit. I had not expected this at first, but the cast is actually very machinable. After driving the old roll pin out of the original tooth belt pulley, I was now able to fit the bored out new pulley to the shaft. But this pulley has no flanges and also no hub that would be sufficient to reinsert the roll pin so that the pulley would actually be fastened to the axle. Well, this is where the aluminium round stock pieces come into play that I brought home from the scrapyard. After using a small center drill bit, a number of drill bits of increasing size, I used to drill a 20mm hole through the round stock, before the part is then also faced off. After that, the diameter is reduced to create a hub that will accommodate the roll pin, connecting hub and shaft. And with that being done, a parting tool is employed to separate our new part from the stock, leaving a collar that will act as a flange on one side of the tooth belt pulley. The workpiece was then turned around and the inner diameter was widened on one side with a boring bar so that the smaller hub of the cast iron pulley will fit inside. In the next step then, a number of holes are drilled using the drill press so that 4 M8 Allen screws can be used to connect the two parts together. The rolling pin can now be punched back in, fastening the new pulley on the shaft. And in order to prevent the belt from slipping off on the outward facing side, a 3D printer was then used to make a second flange that was later glued to the open face of the pulley. I made two identical pulleys like this for the two trapezoidal screws. But we also needed to adapt two more of these crankshaft pulleys so that they would fit the stepper motor axles as well. But unfortunately, with a 14.5mm bore on a 14mm shaft, we were facing a difficult situation. Since I had found a whole number of those aluminium round stock pieces over the years, I went along and tried the same method as before here as well, and all in all, this was hours of work. But with the inner diameter of the actual pulley being too wide, the aluminium hub would be the only part actually holding the pulley on the shaft, and it was very hard to make it run true this way. These pulleys would work alright, but I always try to learn a general lesson from every project and every problem I face. I try to find methods that I can use over and over again in the future, and that is why I actually put these pulleys to the side and modified two more of them in a different way. I bored out the diameter to 20mm and then used some brass round stock offcuts that a viewer had sent me a while ago. I inserted a 14mm drill bit into the tailstock chuck and drilled a 14mm hole into the piece of brass, before turning the outer diameter down to 20mm so that it would fit right into the bore of the toothed pulley. In the next step then, the pulley was brought over to the drill press, where I started to drill three 3.2mm holes into the pulley's cast iron hub, but also going all the way down through the little brass adapter piece. After that, with the workpiece still clamped in the vise, I hand tapped an M4 thread, and after turning the pulley around step by step, I actually did this 3 times, so that 3 set screws can be used to fasten the pulley to the stepper motor shaft. This time, both flanges were 3D printed, but not glued, but rather bolted together. While working on these pulleys, I also learned that one of the M8 threads is actually offset by 5 degrees. Certainly a safety measure to make sure that the timing belt pulley can be only mounted in exactly one way, in its original application of course. And since we have a stepper motor for each of the trapezoidal screws, we also had to make 2 of these pulleys. Now you can imagine that it took a completely unreasonable amount of time to find a way to adapt these pulleys to these requirements. And maybe it would have been worth to just pay the money. But now that I know how to go about it, I have found a cheap and rather quick method to connect parts that were never meant to go together, and it won't be long until we'll need this method again. We're now able to control the 2 trapezoidal screws with the 2 stepper motors. However, this means nothing unless the 2 screws and guides will work in tandem, and in order to make that possible, they need to be connected in the middle. This will be done via this massive linear guide that I bought on a recent trip through the southwest of Germany. This is a used part and it's decades old, but it was the only component long and massive enough to not only go along with the build quality of the other guides, but also work together with that very valuable ball screw that I had found on a scrapyard some time ago. The guide alone weighs 100 kilograms, and it still cost me a couple of $100 even though it's ancient. As you can see here on one end, it is not made from tubes. These are massive steel rods. At the moment it is only sitting on these carriages, riding on those 2 trapezoidal screws though, it's not fastened. We need to find a way to not only attach the guides permanently, but also install the ball screw here as well. This leftover piece of a 14mm thick steel plate is also a scrapyard find. We will make 2 parts from it that will serve a double purpose. They will act as spacers between the 2 linear guides, and they will also accommodate the 2 bearings for the ball screws. I used an angle grinder for this job, but I hope this is the kind of thing that will soon be taken care of by the CNC plasma cutter. With these heavy plates bolted down to the carriages on the left and right side of the table, we have created another solution that could be disassembled again in the future. But so far, these parts only connect the two screws of the Y-axis with the ball screw. The linear guide for the X-axis movement is still simply sitting on there. This will be taken care of by using two steel angle pieces. The cast iron parts on the two ends of the guide will be bolted to these angle pieces, and that is why a number of additional holes had to be drilled into both the angle pieces and the cast iron parts. And after bolting these angle pieces to both ends of the guide and align everything as carefully as possible, it was now time to TIG weld these parts to the 14mm steel plate. I tack welded these parts on both sides of the guides before actually finishing the welding job, so that I wouldn't have possible warpage or stresses on just one end while the other opposing end is still loose. I created a very solid connection here, while the bolts will still allow me to adjust the exact positioning should we run into alignment issues later. It would now be possible to test if the two linear guides of the Y-axis are able to work in tandem without causing stresses, but before doing that, I actually wanted to prepare the ball screw to be connected to a third stepper motor. By now I had become rather efficient in adapting those crankshaft pulleys, so I knew what to do. I bored out the inner diameter of another pulley to 20mm because that was the biggest drill that I had at hand. After that, I used a boring bar to widen the ID to 25mm so that it would fit on one end of the ball screw. Just like before, I pre-drilled and hand-tapped a number of M4 threads into the hub of the pulley in order to fasten it to the screw, and that all worked out just fine. Since I had already used those two Japanese NEMA 34 stepper motors for the Y-axis, another scrapyard find was needed for the X-axis. My first idea was to use this old German-made stepper motor of similar size for this job. It still had a worm gear on its shaft that I first needed to remove. There also is already an adapter piece sitting on the shaft as well that we can reuse though. However, it's held by two pins that were once punched through the shaft, and their heads are somewhat proud of the outer diameter, and I have to grind them down. That's why I changed the set of jaws on the 3-jaw chuck and clamped the motor shaft into it. Since the shaft is protruding from the backside of the motor as well, I was able to use the tailstock chuck to run the motor between chucks, if you will. This way I was able to use a hand file to even out the surface. And now, you guessed it, another crankshaft pulley was bored out to 16mm to fit on that motor shaft. The more often I do this, the better I get at it, and the more it will pay off to have only paid $5 for the original part. To run the three motors at the same time, I also needed a sufficiently powerful power supply though. This reminded me of another project that I worked on a good while ago. One day I had found a ton of identical office computer power supplies on the scrap, and I had actually integrated 4 of them into one common enclosure. Normally it is not possible to just connect several computer PSUs in series since their output voltages are not floating voltages. What does that mean? The minus pole of the 12-volt power supply is internally connected to the metal enclosure, which is also connected to protective earth. In other words, if you run several of these power supplies on a common line, where they all have the same PE connection, all their minus poles on the output side are also already connected to each other. The same is true if you have no PE connection at all, but when the metal enclosures of the PSUs touch each other. By removing the internal connection of the minus pole of the output side to the enclosure, it becomes possible to connect them in series. This way you can get 12, 24, 36 or 48 volts from this device. I do, however, not recommend to do this, as it might be dangerous. Long term, I will probably build a mains transformer power supply for the motors anyway. In the meantime, I had also made these big plastic parts here that will allow me to just bolt the NEMA 34 stepper motors to the frame of the CNC table. I think they are rugged enough, but I still want to make better ones from steel sooner or later. And with the electronic controls hooked up experimentally, I was now able to test the Y-axis drive and check for possible misalignment and also find out about possible maximum feed rates, etc. By moving the drives back and forth many times and slightly correcting the position of the guide assemblies and also scraping off some remaining hardened lubricant from decades past, I was able to get the Y-axis movement really smooth and everything worked as planned. The imbalance you're hearing comes from the first set of pulleys that I made for the steppers. They simply didn't run true enough. This problem was taken care of though by installing the second variant with the brass adapter pieces later on. And after freeing everything up, especially from the old lubricant, I was able to get much higher feed rates than what you see here. But at least for milling, the actual feed rates in action will actually be very slow anyway. For the next few important steps, a whole number of custom parts had to be made. To make that possible, I was planning to use the smaller CNC plasma cutting table that I built in the last episode. But in order for it to work smoothly, a few upgrades were necessary. Cutting so many parts creates an enormous amount of sparks, metal vapor and fumes. Next to a fume extractor and proper ventilation, a metal pan filled with water, which will catch and quench the metal droplets emitted by the plasma cutter, helps a lot in limiting the fumes, while also reducing fire hazards. At first, I had thought that it might be a good idea to reuse these galvanized steel shelves here to somehow form a basin out of a number of them. But that turned out to be a completely impractical plan. So I bought a piece of galvanized steel instead and started to form a water pan by bending over all four edges. In forming the metal sheet according to the required dimensions, I had to improvise, using pieces of wood, among other things, to get the job done. I used MS polymer to make the corners watertight, employing a single rivet in every one of the four corners to hold the sheets in place until the adhesive was dried. After that, the pan was filled with water. 3 or 4 centimeters of water seemed to be enough, by the way. I also replaced the old screw clamp style ground clamp with another style of clamp, so that I would be able to connect the workpiece without accidentally lifting it off the window well grates that I use as a support surface. Another issue is the following. The specific plasma cutter that I'm using is supposed to be used for contact cutting, meaning that the nozzle sits on the workpiece directly while cutting with no air gap in between. I plan to actually add another stepper motor and automate the Z-axis as well. But for the time being, a simple piece of plastic and a spring will ensure that the nozzle sits on the workpiece while the force pushing down on the nozzle will be minimized. This way we can cut sheets while maintaining contact without unnecessarily scraping or scratching the nozzle or the workpiece. I also recalibrated the machine by making sure that the parameters used in Gerbil are really precise. I also found out about the maximum feed rates and accelerations that were still practical for jogging the machine around, for example. Even more upgrades will happen in the future, but this ought to be sufficient to get the job done. So the first part that I'm making on the plasma CNC table is a rectangular piece of steel with rounded corners. It'll act as a support and mounting plate for the third stepper motor of our big CNC table. It needed a few holes drilled as well so that it could be mounted on this cast iron part at the end of the big linear guide. We would now be able to drive the ball screw, but there is one more issue. These are two different stepper motors that I both found on the scrap and that I want to try to use for this purpose. Only problem? In their current configuration, they don't have enough torque to move the screw. Why is that? Well, these are 8-wire, 2-phase bipolar stepper motors. The 8 wires are the 2 ends of 4 coils. And in the current configuration, we have 2 pairs of 2 coils in parallel, acting essentially like 2 coils. Then we only have 4 connections on the ends of these wires. Connecting the coils in parallel means that the motors are configured for high speed, low torque operation. But we want the opposite, which is low speed but high torque. And that is why I'm rewiring them so that the sets of coils are connected in series rather than in parallel. This is only possible with 8-wire 2-phase motors, while it is not possible with 4-wire steppers like the ones we used in the smaller CNC table in the last video. 6-wire steppers are like 4-wire types, but with additional center tabs, by the way. Next, we needed to do more plasma cutting. In order to create a sled that will connect to the linear bearings and the ball screw nut, we need 2 large rectangles made from 6mm steel plate. This is also material from the scrap, by the way. And as you can see, the water pan is also doing a pretty good job in catching most of the sparks. Another somewhat more complicated part is this one here, which will be connected to the ball screw nut directly. It will be responsible for actually moving the sled around. But first, the 2 plasma cut rectangles are welded together in a 90-degree angle, also incorporating 2 heavy angle pieces that are supposed to give the part more rigidity. This welding job required a lot of patience and double and triple checking the angles, because I want to make sure that whatever we will connect to the sled will be properly aligned. And here you can see the rough form of the sled and the little mounting plate already being bolted to the ball screw nut. And next, a number of holes were drilled into the bottom part of the sled where it will be bolted to the linear bearings. But the sled will also have to connect to different attachable and height adjustable tool holders, where we can attach a plasma cutter or a router, for example. In order to make that possible, the face of the sled is first scribed, and then a number of 8.5mm holes were drilled. And then M10 threads are hand tapped into it. And this is where the linear guides will sit on that bottom part of the sled. It was already bolted down on one side before the holding plate is welded to that plate as well. I only tack it in place at first because, as always with this project, I have to make sure that the alignment can be adjusted before making anything too permanent. But with that being done, it was now possible to bolt everything tightly in place, and the sled is now operational. Our sled could now be used to attach any number of tools to it. One idea is to use it as a plasma cutter as well. It would certainly allow for larger workpieces than I could work on the smaller CNC. But since it's so ruggedly built, I also want to use it for CNC milling. And since I just happen to have this old router here in the shop, this is one of the first tools we're going to fit to it. What is it though? Well, it's a router named MOF11 built by the German company ELU in the 1950s, and it's like the granddaddy of today's routers. It is massively built, and with a power rating of 2000 watts, we should be able to do some damage with this thing. The old router bit it came with has an M12 thread, but luckily I was able to buy a collet that screws right on the old M12 thread and will now allow me to connect modern 6 and 8mm router bits to it. I have an assortment, but I also ordered additional ones for milling metal as well. In the next step, I started to make a tool holder that will allow us to attach our plasma cutter or this router to the CNC machine. It consists of several plasma cut parts, and you can see here that I usually try to design the parts so that they can be cut in a closed loop. Piercing through the steel wears out the expensive nozzle rather quickly, and that is why I'm trying to minimize the number of piercing operations needed. While the first part here will hold the router or the handpiece respectively, the second part will serve the purpose of a height adjustable mounting plate that will be bolted to the face of our sled. In order to make that possible, these parts were welded together and additionally reinforced. The router can be attached to this part by bolting it down with an M48 nut. But since this is not the kind of part you just have lying around, I made one on the 3D printer, but I also ordered one made from steel for the future. A holder for the plasma cutter handpiece was also designed using a 3D printer. And even though it must seem like we're almost ready for a test here in the video, in reality I was still about a week away from doing that. But let me make it quick since I know that you guys want to see it in action. So a bunch of flat stock had been wire wheeled and cut into sections. Angle pieces were welded onto the inner walls of the I-beam frame. They serve as rests for those flat stock parts, and those were then also welded to these angle pieces. And here is where our window well grates were installed. It will be possible to remove them and go for another solution in the future, but they will allow us to do plasma cutting here. And since I have to look at this thing all the time now, I also took care of the remaining rust and applied a paint job. The feet of the columns of the support remain unpainted because this is where another water basin will be added soon. In the meantime, I also had to calibrate the parameters of the machine. You have to tell Gerbil how many steps equate to a given distance in the real world. The steps to distance ratio is different for the different screws. One revolution equates to 16 mm advance on the ball screw, but only 6 mm on the trapezoidal screws. But that is no problem, and it is really easy to change these numbers in Gerbil. This is necessary to make sure that the measurement of the workpiece will actually be the same as the one you typed into your CAD software on the computer. And since you've seen enough plasma cutting action in this video already, we're going to test the big machine by milling wood and different metals instead. We start with a 6 mm in mill in a piece of beechwood. What I'm doing here is some simple passes, curves and circles. And what might have looked nasty at first glance are just chips stuck in the grooves here. The slightest touch with some fine sandpaper or even just your fingertips reveals a pretty nice result for a first test. And here is an anodized aluminum plate that I found on a pile of trash a few years ago. Unbelievable, I know. We will certainly use it for something useful soon, but let's do some tests on one end of it at least. The 6 mm carbide mill cuts through the aluminium with ease. And I think this result is pretty nice as well. What happened here though? Well, that was my fault. I accidentally set the feed rate 10 times higher than what I wanted to type in, and well, the mill got stuck in the workpiece, so I had to start over. But at the lower feed rate, we got great results. I also wanted to test if the machine is able to cut through the entire 10mm aluminum plate, and that works as well. By the way, after having milled through the beechwood, the old EMI filter inside the router gave up for good. I had to open it up and install a replacement part. I actually knew that this would happen and should have done it right away. If you have one of these, replace the filter please. Anyway, with the new filter installed, we were back in action, and I even tested milling 3 or 4mm deep grooves into steel. And even that worked. Well, I'm pretty sure that I will still have to work out a lot of kinks over the coming months, and I will probably have to beef up some parts, remove a vibration here and there. Many upgrades will come along the way, that's for sure. But long story short, both machines work now and can be used to make parts. Everything else, like measuring and refining tolerances and all that, will have to be worked out over the coming months. Believe me, you have no idea how much work it was to just get this video out. There is just so many different aspects to it when you go from a rusty hunk of scrap to a working CNC machine. Who'd have thunk, right? So did you like this video? Then please give it a like. It would really mean a lot to me. Anyway guys, this is definitely not the last time you have seen these machines. However, I have surgery coming up in about a week from now. It's nothing serious, but I'll spend some time in a hospital and might need some weeks to get back on my feet completely. The next video will just have to be a much smaller project. Probably some neat repairs of some older equipment. This actually couldn't come at a worse time though, since, well, it will mean that I will make much less money for a while, and I have kind of overextended myself recently anyway to gear up the workshop for the future. Thing is, I do live in Germany, so you might think, hey, this guy gets money when he's in the hospital, right? That's not right. I'm self-employed. I don't get squat if I don't work. Well, anyway, I'm planning on making videos as long as I live, but I also need to build more real-life capabilities here in the workshop so I can make more money independent of YouTube revenue. The last episode was one of the most expensive, hardest to produce, and in my opinion best videos I ever made, yet it only got half the views of the one before that. What in my opinion should have been the epitome of 10 years of work on this platform felt like a punch to the gut. Imagine planning something for years, collecting the parts, making the plans, then finally executing it, and the platform you rely on buries it after 2 days. And that's unfortunately what happened. Have I given up? Nope. Otherwise I wouldn't have doubled down by producing this episode, which was even harder to make. So in other words, I rely on your support at the moment, and I would really appreciate if you could make a donation if you can afford it. A link for that is under the video. Or maybe consider becoming a supporter on Patreon under patreon.com/tpai. See you soon with the next project.